Hello all and welcome to this video where we look at determining the rules for exponential and log functions. So this is just like every other exercise we've done where we've been determining a rule where we have a certain form of the equation, we're given a couple of coordinates, and then we effectively need to use, normally it's simultaneous equations to solve and find what the base or original equation was. This is a little different to the prior ones, where the prior ones, especially we think of quadratics, we could deal with the polynomial form, we could deal with the general form, we could have turning point form, we can have intercept form, and we'd make targeted selections which forms we wanted to use or substitute into to make our solving of the simultaneous equations a lot easier and get a few of our values or coefficients in the equation a lot quicker. For logs and exponentials, generally you're just going to be given the form to use. You're not going to have to use that bit of critical thinking to go, which form do I need to use? You're going to be given the form. So let's have a look at that straight away. The one thing I want to state, the only hard thing about this is the algebra, especially when we're not quite used to, or it's not as common dealing with logs and exponentials, especially if we're dealing with actually e itself and natural log, so log to the base e. We just need to keep reminding ourselves that e is just a number. It's just 2 point something. We don't need to get wrapped up in saying it's a variable. Oh, what do I do? The rules of mathematics don't change. It's still just a number. We can do all our things. We get to use our exponent laws. We get to use our log laws. Don't freak out when you see the e there. So let's jump in. An exponential function has the rule y equals a times e to the x plus b, and has the coordinates 0, 3, and 2, 4 are on the graph of the function. Find the values of a and b. So what we're going to do first off is just substitute those points in. That's our x1, y1, this is our x2, y2. Sub them both into this equation of the form, we're going to get two equations. So, let's substitute in coordinate 1. We're going to get 3 is equal to a times by e to the 0 plus b. So that was substituting in coordinate 1. If we substitute in coordinate 2, we're going to get 14 is equal to a times by e to the 2 plus b. So there's our two equations. Now for this problem, what I'm going to do is show you, I've already got all the working out already in there, so you can jump in and have a quick look on this next slide. I will talk through it a bit, but then the slide after, we're going to start another problem from completely scratch and work through all the algebra. So there's our two equations, equation 1, equation 2, and I've got them written up here at the top. Okay. Now, when we're dealing with exponentials, there's two ways we're generally going to go about it. If we're lucky enough to have one of them to the power of 0, which we are in this case, because anything to the power of 0 just becomes 1, that exponential disappears. It makes our life a bit simpler. We can use subtraction or addition. In this case, we've got a plus b, so we're going to do a subtraction to get the b's to cancel, then we're only left with a's, which is all of this section here. So that works nicely for us. So we can do that subtraction, cancel the b's, so we're left with, we're doing 2 take away 1, so we're left with 11 is equal to a to the squared, take away a to the 0. We can take a out as a common factor here on this line, and then divide that side by e to the 2 minus e to the 0 in brackets, and divide that side over there, and that's how we get our final answer for a, which is right here. Okay, and this is what I was saying before. It still has an e in it. That's fine. This is technically a number. We don't have to solve any further. That's that. We can note though that this e to the 0, once we've got it in the division over here, we've just turned it into a 1, which is what it is. Okay. So that's getting a. So we're done. That's a. That's as far as we need to go for a. It doesn't look nice, but that is a number, and you can stick in your calculator and figure out what that is as a decimal. The other thing we can do is if we look at 1 and then do that simplification, we turn e to the 0 into just 1, we get a nice simple equation, 3 is equal to a plus b, which we can then rearrange to get b by itself, and we can substitute our a into this, okay, because this is just a number. We can substitute into that, which is what this is calling for here, and then doing all this algebra work is simplification. There's a lot of work here algebraically, so what we can see is what we've done is this 3 here, we have converted that. 3 is the same as, we could technically say that's the same as 3 times by 5 on 5, because that's just 1, or the same as 3 times by x on x. They will cancel, or just it's still 1. But what we want to do to be able to combine these two terms, because we've got a subtraction, we need to get common denominators. So in this case, we're going to turn our 3 into 3. Look at the denominator here, e squared minus 1 divided by e squared minus 1, because those e squared minus 1s would cancel or just become 1. But by doing that, that allows us to combine those two terms. We can combine our first term with our second term, which is what's happening in this line here. Just doing a fraction subtraction. Simplify. So that's the fraction. This is the simplify. Actually, I might put subtraction there. Okay. And that's as far as we need to go. Again, it looks nasty, but that is the answer. You could maybe try and factorize this top term, factorize the bottom as a difference of perfect squares, but in essence, that's as far as we need to go. And then we have our final two answers for A and B. Alright, so let's have a go at this one. So we want to find the values of A and B such the graph is y is equal to A to the e to the negative bx goes through the points 6, 30 and 9, 5. Okay, so let's substitute those in. So substituting in the first point to get equation 1, we're going to get 30 is equal to A to the e to the negative 6b. And substituting in equation 2, we're going to end up with 5 is equal to A to the e to the negative 9b. So there's two equations. Now we need to look at these two and see what can we do to get the a or the b to cancel. Well, the b's in the exponent, so that's a dead set giveaway that we can't get that to cancel out straight away. So we've got a coefficient term a and a here. So since it's a coefficient, if you think to normal simultaneous equations, maybe you have 3 is equal to 5x and 7 is equal to 8x. That's actually not a great example because they're linear equations. They don't have two variables. But if you do think back to simultaneous equations, when we have coefficients like this, what we can do is divide each of these two equations by each other, and that would then allow us to cancel out that coefficient. So what I'm actually going to do is 1 divided by 2. So we're going to end up with 30 equals a to the e minus 6b, all divided by 5 is equal to a to the e to 9b. And we can quite clearly see coefficients cancel. Lovely. And we can simplify this a little bit further. 30 divided by 5, that's just 6, is equal to e to the negative 6b divided by e to the negative 9b. And hopefully maybe this is looking like something we have done a little bit before. It still looks a little bit convoluted, but we can simplify this. If we go all the way back to, where's our index laws? Here we go. If we have two exponents divided by each other that have the same base, we can combine those and just subtract the indices. So we can apply that one to this case. So let me write that rule up over here. If we had a to the x divided by a to the y, we can rewrite that as a to the x minus y. Our base in this case is e, but it's still a common base, so we can use that form as index law. So this is going to turn to e to the negative 6b, take away negative 9b. And this is a little gotcha bit there. Just to be careful with the signs, we're technically taking away negative 9b. So we can simplify that is negative 6b, take away negative 9b, that turns into positive 3b. And what can we do from here? We're trying to get b by itself. That's what the whole purpose of this algebra steps is, trying to get b by itself. To get rid of this base e, we could take the log of base e of both sides. So take the log base e of 6, and we take the log base e of e to the 3b. And if we look at our log laws, there's two ways we could go about this. Log to the base e of e is just 1, and we're left with the 3b. But technically what is actually happening, if we go back and look at our log laws here, is we would be using log law 3. And I talked about this in a previous video. This is where this starts to come up. So we had log to the base e of e to the 3b, I think, on that previous equation, yeah. So what we can actually do, this p up there is our 3b. We can bring that out as a coefficient in front. So we would be left with, bring the 3b out in front as the coefficient, and we're just left with log to the base e of e. And that is asking us, log to the base e to what power gives me e inside? Well, that's just 1. Log to the base e of e is 1, so all we're left with is 3b. All of that bit cancels out. So let's go back to our problem. So we now have log to the base e of 6 is equal to, I may as well write that, step 3b, log to the base e of e. So log to the base e of 6 is equal to 3b, and we're now almost there. Just going to come up here. I'm going to divide both sides by 3. So I get log to the base e of 6 divided by 3 is equal to b. So there's our b, finally done. We can't simplify this 6 over the 3. You can't do some cancelling, just have a 2. That 6 is inside the log function. You can't simplify like that, just want to clarify. So we've finally got b. That's done. What do we do from here? We have to, like normal, once we find one of the variables, we substitute that back into one of our original equations to solve for the other variable. Now, which one are we going to substitute into? One thing I want you to notice is we've got log to the base e of 6, and this one over here has e to the power of, it's a negative 6, but it's still a 6 nonetheless. And we're going to be putting this log, all of this, in this power. So log to the base e of 6 and there's negative 6, that's just sort of screaming that there might be something here that is going to work out a little nice for us. So let's do that. So we're going to substitute all of this into equation 1. So we're now going to get 30 is equal to a to the e to the negative 6 of log to the base e of 6 all divided by 3. There we go. So again, it's not pretty looking, but we can do some simplification. The negative 6 with that division by 3, we can simplify that. So we've now got 30 is equal a to the e to negative 2 log to the base e of 6. Okay. And what we're going to do here is we're going to again use, where's that log law 3. We're going to use this in reverse now. Instead, we've got, in our situation, we've got log to the base e. Where is it? Got negative 2 log to the base e of 6. Got negative 2 log to the base e of 6. And we want to move this, get rid of the negative sign and the 2, because all of this is above, it's e to the power of all of that. And if we get this -2 out of the way, we can do a simplification of the e to the power of log base e. But how do we move this -2? Well, or at least the 2 to start with, we can use log law 3 in reverse. Got a coefficient, what we can actually do is put it as the power up over here. So I can turn this into e to the negative log to the base e of 6 all squared. That's equivalent. So let's go back to our problem. So this is going to turn into, let me go back to my black color. 30 is equal to a to the e to the negative log base e of all 6 squared. So that's going to give me 30 is equal to a to the e to the negative log base e of 36. Okay, so we've almost got that ready to simplify down, but we've still got this negative sign in front of the log. And I just want to remind you of, if we have one of the index rules, was that if we have a to negative b, we can write that as 1 on a to the positive b. We just move it down into the denominator and change the exponent from a negative to positive. So we can actually rewrite this as a is equal 30 is equal to a on e to log to the base e of 36. Yeah, we've moved our exponent or our whole index. We've moved it into the denominator, and that allows us to change the sign of the index from a negative to a positive using this index law here. And now we're finally at a stage where we're getting really close to simplifying. If we have e to the power of log e, or actually if we have a to the power of log base a of whatever we want, let's just put x there. That simplifies all down to just x. All of that effectively cancels out, and that was at the very end of the last exercise. That rule is written here. Okay, a to the power of log base a of whatever, all of that cancels out, and we're just left with whatever the log was being taken of. So this simplifies into 30 is equal to a on 36. And we can multiply both sides by 36. And we get a is equal to 1080. And that's it. We have found b, which was up here, and we have found a, which was here. So if we really wanted to, we could then finally write the equation. It's not going to be pretty looking, but we can write it. We get y is equal to 10,080 e to b was negative log to the base e of 6 all divided by 3 times by x. Yeah, there's your equation. Not nice, but there it is. And that's it for this exercise. So there's 2 things to look out for when solving these exponentials. Actually 3 things. First thing, if you get a nice situation where you've got a adding of a b or c or whatever the variable is outside of the exponent or log at the end, then you're going to use a subtraction to help cancel those out. If you don't have that and you've only got coefficients, you're going to have to use a division to cancel that out. And the third thing, you're going to struggle with any of these problems if you don't know your log laws and you don't know your index laws. And that's why we spent so long practicing them. That's it. As always, if you have any questions, please email or put a comment below or ask as normal. Thanks and see ya.